So let's take a look at the whole idea behind conservative forces and potential energy. So if a force is conservative, associated with it is a value of its potential energy. And the idea behind energy conservation is that energy is neither created nor destroyed. It can only be converted from one type of energy to another type. And so we'll start off with some amount of kinetic energy and some amount of potential energy, and through a process of movement we'll end up with a different amount of kinetic energy and a different amount of potential energy. But the sum of these energies will be the same before and after. Now this is only going to hold true if there are no non-conservative forces doing work. If there are non-conservative forces like friction doing work, then I need to account for that. And this is really nothing more than the work and energy theorem that said you start off with some kinetic energy, you have some work done, and the potential energy really is the opposite of work being done, and you end up with some kinetic energy, and in this case some potential energy as well. So let's take a look at an example of how to do energy conservation. When I do energy conservation, I like to use bar graphs. And here's the idea behind the bar graphs. Let's assume that I have a ball and I'm going to drop it off the top of a building, and this building is at some height y naught, y sub 0 above the ground. And I'm just going to drop the ball, which means the initial velocity is equal to 0. And I'm interested in what's the velocity when it hits the ground. Now the idea behind energy conservation is that I have an initial kinetic energy, which is going to be equal to 0, because there is no velocity, so 1/2 mv squared is 0. But I'll have some final kinetic energy at the ground, which is 1/2 mv sub 2 squared, v sub 2 being the second velocity, the velocity at the ground. The potential energy here, if I ignore air resistance, the potential energy is only the potential energy due to gravity. Now the potential energy due to gravity, which I'll label as v sub g, is equal to mgh, where h is the distance above some 0 point that we call the datum. So at the datum, h is equal to 0. Some books will call this y or y sub 0. I'm just going to call it h as far as the potential energy is concerned. So the question mark is, where is the datum equal to 0? Well, the beauty of this is it can be anywhere I want. So I'm going to put the datum right here at the bottom. So that is the point where h is equal to 0. And we'll see in a minute it doesn't matter where I put the datum, but let's just put it there at the bottom for starters. So at the top of this building, the potential energy due to gravity is equal to mg times the height, which I have labeled y sub 0. At the bottom, the potential energy due to gravity, which I'll go ahead and subscript with a 2, here I'll put a 1, this is going to equal 0 because the height at the bottom is equal to 0. That's where I've placed my datum. So T1 plus V1 equals T2 plus V2. The initial kinetic energy is 0 plus mg y sub 0, and that's going to equal 1/2 m v sub 2 squared plus 0. And so my equation becomes mg y sub 0 equals 1/2 m v sub 2 squared. If I cancel the m's, so the masses divide out on both sides, so notice the velocity does not depend on mass, but we know that already. And let's bring the 2 over to the other side, so I'll multiply both sides of this equation by 2. When I do that, I get 2g y sub 0 equals v sub 2 squared. But this is no different, especially if I add a v sub 1 squared here. This is the same equation we saw back in the constant acceleration case, where in this case the acceleration is the acceleration due to gravity, and that initial velocity was 0. Even better, the initial speed was 0. So there's my answer. Now, let's repeat this problem. So I still have a building with a height of y0. But for the sake of argument now, I'm going to put my datum here at the top. So my datum is up here. So this is where h is equal to 0. I'm still dropping the ball with some velocity 1 equal to 0. And so the first kinetic energy, the kinetic energy at the top, is equal to 0. But since my datum is 0 at the top, then my potential energy is equal to 0 as well, because potential energy is mgh. But at the top, that's equal to 0. So down here at the bottom, I have some velocity v2. So my kinetic energy is 1/2 m v2 squared. And my potential energy, v2, is equal to mg times negative y sub 0. Why negative? Because I am below the datum. So this direction is negative y. I am below the datum. And so T1 plus V1 equals 0. Neither of them have any value. Well, this is going to equal T2 plus V2. And so 0 equals 1/2 m v sub 2 squared minus mg y sub 0. But I can bring the mg y sub 0 to the other side of the equation. That's just algebra. And I get mg y sub 0 equals 1/2 m v sub 2 squared. Well, just as on the previous page, the masses go away. Let's multiply both sides by 2, and I get 2g y sub 0 equals v sub 2 squared. The exact same equation. This equation is exactly the same as this equation, even though the datum was at a different point in each of these two examples. Now, where do the energy bar graphs come into play? If I start with this example, I can draw an energy bar graph. Looks something like this. At the top, there's two kinds of energy. There is kinetic energy, and there is gravitational potential energy. At the top, there is no kinetic energy, but there is gravitational potential energy. And so what I'm going to do is I'm going to give that a value of 2 bars. Doesn't matter how many bars I give it. I'm just going to give it a value of 2 bars. At the bottom, there is going to be kinetic energy. The object is now moving. But because the datum is at the bottom, the potential energy due to gravity is equal to 0. And so at the bottom, I have 2 bars of kinetic energy. Why 2 bars? Because at the top and at the bottom, the number of bars of energy must be the same. Energy is conserved, the number of bars needs to be the same. And so I can associate now with my energy bar graph equation. 0 plus mgy naught equals 1/2 m v sub 2 squared plus 0. So what I do is I associate a numerical value or an equation with each of the types of bars that I have with my energy bar graph. And so this equation is, of course, identical to this one right here. But what the energy bar graphs do is they give you a visual interpretation of what's going on with energy conservation. In this scenario, it's still going to work pretty much the same way. At the top, I have no kinetic energy, and because the datum is at the top, I have no gravitational potential energy. There are no bars. At the bottom, the object is clearly moving, and so I'm going to have some kinetic energy. The potential energy due to gravity, V sub g, also has a value, but V sub g is negative. And so this has got to be below the axis. I'll put V sub g up here. And you'll see I have positive 2 bars of energy on kinetic and negative 2 bars of energy on the potential. That adds up to 0. So I end up with 0 bars on the left and a net of 0 bars on the right, meaning this value plus this value have to add up to 0, which they do. I could even choose a middle point halfway down that tower, and I would see that I have some kinetic energy, maybe 1 bar of kinetic energy, I better have negative 1 bar of potential energy. Total energy is equal to 0. I would have 1/2 mv in the middle squared plus mg times negative y0 over 2. That's my potential energy. This would have to add up to 0. That would have to equal 0. I won't get the same velocity as I do here because I haven't fallen as far. But the idea with the energy bar graph is that my bars have to be the same. That is, my total energy has to be the same in every scenario. Let's do one more problem. Let's assume I have a mass on an inclined plane, and we're going to attach a pulley, a cord. We're going to attach a cord to that, and then we're going to hang over the side another mass. So this might be mass 1, and this might be mass 2. And you can see by the setup, I'm going to want mass 2 to be large so that it pulls down and mass 1 goes up the incline. So this would be at some angle theta. We'll make this some distance d along the incline. All right, so what I'm interested in is as M2 falls to the floor, how is my energy changing? Well, the idea is this. If I use energy bar graphs, I'm going to call this position 1, and later on, mass 2 is on the ground, and mass 1 has gone up the incline. It's the same incline. So there's position 1, here's position 2. Okay, position 1 over here, position 2 over here. What do my energy bar graphs look like? Well, here's the deal. I have 2 masses. So when I look at the energy bar graph, I'm going to have a kinetic energy for mass number 1 and a kinetic energy for mass number 2. Now initially these are both 0. I'm going to have a potential energy for mass number 1 and a potential energy for mass number 2. And I can see that M1, let's put my datum right here at the bottom. And I should point out, and this is really important, the datum does not need to be the same for mass 1 and mass 2. In this particular example, it's convenient to do that, but it does not need to be the same. But if I make my datum here at the bottom, the potential energy for mass number 1 is 0. Mass number 2, however, does not have a 0 potential energy. So let's just say it has 5 bars of potential energy. Then what happens over here? Well, mass 2 has fallen, mass 1 is rising. Clearly mass 1 has a certain amount of kinetic energy. We'll just call it 1 bar. Mass 2 is falling, it has not yet hit the ground, so it also has some kinetic energy. We're going to make mass 2 bigger, so I'll give it more bars. Now, mass 1 has risen, so it's got to have some potential energy, and mass 1, so there's potential energy for 1, mass 2, rather, has not risen. It's fallen, and now it's at the datum, which is still down here. You cannot move the datum once you have it set. Mass 2 has 0 potential energy. And so I have 5 blocks of potential energy over here and 5 blocks of potential energy over there. They're the same. Write out the equations. 0 plus 0 plus 0 plus mass 2 g, and we'll call this distance y sub 0, equals 1/2 mass 1, the velocity of 1 squared, plus 1/2, because you notice there's bars there, there's blocks there. I cannot have a 0 energy. Mass 2 times the velocity of 2 squared plus mass 1 g, and if this one fell a distance y0, this has gone up a distance y0. But remember, gravitational potential energy only cares about the height. And so the height is going to equal y0 times the sine of theta. I'll let you work on that trig, and then plus 0. And so there's my energy equation. Of course, I can ignore the zeros because that's what they are, 0. There's my energy equation associated with my bar graphs, and that allows me then to solve this equation. Of course, in this particular example, V1 equals V2. And again, my height h equals y sub 0 sine of theta. Okay, you think about it this way. Here's y sub 0, there's h, and there's theta.